Hi, I'm going to tell you about. Oops. Yes. Okay, and I'm generally interested in theoretical computer science. Okay, so let me start by telling you of a problem on random graphs. So suppose I sample a graph G at random from the Erdős-Rényi model, where I choose every edge to be included in the graph with probability half independent of others. Okay. If you estimate the size of the largest clique in this graph, clique in a graph is a subset of vertices such that every pair of them are connected in the graph. So the size of the largest clique in it, it's going to be of size about 2 times log n. Okay. Now, if I give you such a graph, there is a short way to convince anybody that there is indeed a 2 log n size clique in it, which is by just furnishing the vertices of the clique, because I can efficiently check if every pair of them are connected in the graph that I'm given. Okay, great. I'm going to ask the flip side of this question. In a random graph, the upper bound on the largest clique is at most 2 log n, which means that if I ask you, is there a 3 log n size clique in the graph, for example, there is none. I ask you, can you give a short proof that is a certificate of this fact? And whenever I say short proof, I mean a short proof, meaning the size is polynomial in the size of the instance, so polynomial in the vertices of the graph n, and it can be verified efficiently using polynomial time procedure. So there is a fast algorithm that can access the proof and convince itself that the given graph has no clique larger than 3 log n in size. Okay. A further question that one can ask is, when such a proof actually exists, can we discover that proof using an efficient algorithm? Both these are different questions. I mean, the proof could exist, but the algorithm may not, and the proof could exist, and you might actually get lucky and also have an algorithm to find it. Okay? Let me tell you a different question in the same spirit. It is about random constraint satisfaction problems. I'm going to give you an example here. Suppose I give you a set of randomly generated 3 variable linear equations modulo 2. What does that mean? Well, let's say I have n variables. They are supposed to take Boolean values, 0 or 1, and I generate equations as follows. I draw random 3 tuples of vertices, random 3 tuples of these variables, and for, let's say, if I drew 1, 2, 3, then I write the constraint x1 plus x2 plus x3. I choose the right hand side 0 or 1, again uniformly at random, so let's say 1, and I write the constraint that this equation should hold mod 2. Okay? And I generate, let's say, m such constraints independently. Okay? Similar to the previous setting of random graphs, you can show that if the number of equations that I generate, m, are much number of variables, then no 0, 1 assignment to the variables x satisfies more than half fraction of the equations. Okay? And half is somewhat rough, and it depends on what m and n's relationship is, but it's close to half. Okay? And again, I can ask a similar question, right? This is going to be true for most instances that I construct in this way. I can ask, is there a short proof which can be verified using an efficient procedure to convince itself that, for example, no 0.99 fraction of the equations in my instance are simultaneously satisfiable via any assignment. Okay? So now let me give you the disappointing news. Oh, and before giving that, we can also, of course, ask whether such a proof, if it exists, can be found using an efficient algorithm. It's sort of moot because I already told you that I'm going to disappoint you. So yeah, I was somewhat unsure whether I should title it what we know or what we don't know, because the answer is that I don't know the answer to both of these questions that I stated before. If the distribution, so I generated these instances of my problems at random. If instead I was allowed to pick worst case instances, meaning I was allowed to pick arbitrary instances of, for example, graphs or the 3 variable linear equations, then I can use standard conjectures in computational complexity to conclude that the answer to the existence of the short proof question is actually no. Okay? But it's yeah, NP is not co-NP, for example. Yes, yeah, that's why yeah, it's like P versus NP, but it's the so NP is the class of all problems for which you have a short proof. Co-NP is a class of all problems for, okay, let's not go into it, but yes. But it turns out that these conjectured complexity class separations are not enough to derive non-existence of short proofs for problems where the instances are generated via some distribution. So if you don't care about worst case instances but care about the complexity of the existence of the proof in random instances or typical instances, then such conjectures do not yield anything. Okay? And so we are left with the question, what should we do at this point, right? And here is one way to make progress. Okay? When I was trying to understand whether short proofs exist for short certificates exist for certifying various properties that we looked at, we were allowing arbitrary polynomial time verification procedures, right? I was okay with any polynomial time procedure that could verify the proof. Suppose now I restrict this procedure in a certain structured way. I add more structure to the kind of procedures that can be used to verify the proof. Since this is going to be a more restricted setting, I can hope that I'll have arguments to show existence or non-existence of these proofs. At the same time, if I could argue that this restriction in some sense captures many of the strong techniques that we already know, then this restriction may still be sensible in the sense that, okay, it does not give us the answer to the question that we already actually want to ask, but it still gives us some indication about what that answer might be. Okay? So what we are going to see now is one such strong proof system, the sum of squares proof system, which is the title of this talk. Okay? And this proof system applies to a general problem of testing polynomial feasibility. Okay? So let me tell you what that problem is. Suppose you have m polynomials over the reals, n variate polynomials over the reals, p1, p2, pm, and you are given this system of polynomial equations defined by them. Okay? You are interested in finding if there is an x in Rn that satisfies all these polynomial equations simultaneously, and when there does not exist such an x, you want to get a short proof which shows that this system of polynomial equations is infeasible. Okay? This is a very general problem. It may not be apparent right now, but it does capture the two problems that I told you of before. In fact, it captures a lot more. In particular, if pi's are not linear, then it captures the standard linear programming problem. If there is a single polynomial which is quadratic, then it captures the eigenvalue problem, and so on. And in general, if I allow larger degree polynomials, degree greater than 1, then it turns out that it captures many computational problems of our interest. In particular, some of them are NP-hard, which is computer science jargon for saying that we expect the problem to be hard, or in other words, we don't expect short proofs or efficient algorithms to exist. Okay, so in general, which means that this problem captures a lot of computational problems. Some of them are hard. So in general, we don't expect a blanket solution for this problem to exist. Okay. Let me convince you first of all that it does capture one of the problems that I showed you on the previous slide, though. Right? So the problem was of detecting if a graph had a large clique, right? So here is a simple polynomial feasibility program that captures the existence of a k clique in a graph G. And this is really simple. What I want to intend is x as a 0, 1 indicator of a k clique in the graph G. Okay, so I'm going to add constraints so that x always is restricted to an indicator of a k clique. Okay? So to make it a 0, 1 indicator, I add the constraints, degree 2 constraints, that xi square equals xi. This forces xi's to be 0 or 1. To choose exactly k vertices, I add the constraint that some xi is k. And to ensure that the vertices that I pick are a clique, I just need to ensure that if I pick a vertex I and j together, then they always should have an edge between them. In other words, if I pick I and ij don't have an edge, I cannot pick j. So this condition here enforces that. Basically, xi dot xj should be 0, which means that if xi is 1, then xj cannot be 1 when ij is not an edge. Okay? So basically, this polynomial feasibility program, so if it is feasible, then there is a k clique in G, and if it's infeasible, there is no clique in G, which means that if I could solve this problem above or prove or provide a short proof of infeasibility of these equations, then I would be able to obtain a solution to the problem I stated in the slides before. Okay? And similarly, it can actually model the other problems that I said and many others too. Okay. So I was telling you that I'm going to restrict to a certain structured notion of proof in order to make progress on the existence of short proof question. This restriction is going to be what I call sum of squares proofs. Okay? So what does this do? So remember that we had a system of polynomial equations p1, p2 up to pm. A sum of squares proof refuting these equations, in other words, proving infeasibility of this equation, is an identity of the following form. Okay? It expresses -1 as s, which is going to be a sum of squared polynomials, and some pi times qi, where qi going to be arbitrary polynomials. Okay? So suppose somebody proved to you that this identity holds. Let me convince you that this is a refutation of the feasibility, this system being feasible. Okay. So let's see why. Suppose there is an x that satisfies all these equations. Then this some pi qi term has to be 0 because each of pi at x evaluates to 0. On the other hand, the s will always evaluate to a non-negative number because s is the sum of squared polynomials, which means that the right hand side is strictly is non-negative. On the other hand, the left hand side is a negative number, which is a contradiction to the existence of such an x, which means that if such a proof exists, then I can be convinced that there is no x that satisfies this equation simultaneously, right? Okay. Of course, we care not just about existence of a proof, but of a short proof, and later on efficiently a proof that can be efficiently found. So I'm going to put some restrictions s should be of degree at most d over 2, which means that s is of degree at most d. Similarly, the degree of pi times qi should be at most d. Okay. If this is true, then the right hand side has degree at most d, right? And this degree in some sense captures the notion of how complex my proof is. Okay. As you will, I will not go to this, but it also determines the size of the proof. You can show that if there is a degree d proof in most settings of our interest, so when you add certain additional constraints, the number of polynomials required to write such a proof are also n to the d, at most n to the d. Okay, I won't go. Yes, I can bound this capital D and capital M. Oh, actually, capital M is already bounded. So yes, I can bound this capital D. Yes. So, but we will not go into this. So let me first convince you that this at least is a proof. Why is it a proof that the polynomial system is infeasible? Well, if somebody gives you this s and qi's and claims that this identity is true, then you can actually verify it by just going coefficient by coefficient, right? And if the degree of the polynomials is d, then roughly you're going to check into the O of d coefficients. I'm going to ignore the issues of numerical accuracy that come up. Let's sweep them under the rug for now. But essentially, you can get in spirit, you can see that this proof, if it exists and somebody provides it to you, can be checked efficiently. Okay. Great. So that's already what I said. So the one question that should we care about is, should such an identity even, so what we would like is that whenever this system of polynomials is infeasible, such a proof should exist. It turns out that this is indeed true. Nice for us. So and this result is called positive Selin-Sarch, and this is actually a deep result that builds on Artin's solution of Hilbert's 17th problem. And it was sort of generalized to this setting of system of polynomials by Krivine and then Stengel. And essentially for us it says that if the system of equations script T is infeasible, if and only if there is a sum of squares proof refuting it. Okay, so that's great. Whenever we want such a proof to exist, it does exist. What is extra nice is that if the proof has degree bounded above by capital small d, then it can also be discovered by an algorithm that runs in time into the O of d. So if such a proof exists, we also answer the second question, that it can be efficiently discovered. Okay. And again, I'll tell you only a little bit more about this, but we'll not go into details. Okay. So the third condition that we were posing when we wanted to deal with restricted proof systems is, why are they sensible? They should capture at least some strong techniques that we know, and it turns out this is true about it. It captures many of the standard inequalities that we use in our proofs, etc. And these are just like a very small list, but it captures many techniques that are of interest to it, especially in analyzing algorithms in computer science as such. Okay. Okay. So coming to the results, the two problems that I told you, we can resolve their complexity in this restricted proof system. Okay. We can show, for example, that the problem of certifying that a random graph has no clique smaller than even n to the 0.49. Remember that it has no clique larger than 2 log n. But we can't even certify that it has no smaller than root n size cliques without spending logarithmic degree. So remember that the complexity of the proof grows exponentially in the degree, and for a short proof we want this degree to be constant. Okay, so this is saying that essentially the complexity is quasi-polynomial. Okay. Similarly, for the second problem that I told you, an even stronger result holds. This was shown by Grigoriev, who showed that there is no small O of n degree sum of squares proof that shows that the system of equations modulo 2 that I generated are in fact not satisfiable. So a system being all very nice, and then I showed you lower bounds, but in some sense this result can be generalized to arbitrary constraint satisfaction problems. So I told you about linear equations, but it actually generalizes to other problems of the same class called as constraint satisfaction. We don't need to go into the details here. Yes. Yes. So with high probability, meaning for all but an inverse polynomial fraction in n of the instances. Yes. So that was this with high probability part. Okay, so let me just tell you a little bit about why I care about this proof system in particular, because I showed you some results already. So I told you that there is an algorithm that finds it, and if a degree D proof exists, then it can be discovered in n to the O of D time. This algorithm uses semi-definite programming as a black box. So it's in some sense an algorithm that we understand and can be used to discover such a proof whenever it exists. It's a semi-definite program. Yes. And so what's nice about this is the following. It's a general algorithmic scheme that's applicable to many computational problems. This is because it's just polynomial feasibility. Wherever you can encode your problem as polynomial feasibility, which happens to be a very general versatile encoding scheme, you can adapt your problem to fall into this framework. Okay? And it has applications to many fields. It captures many strong techniques and actually has yielded faster algorithms, new faster algorithms for many problems of our interest. Okay, so in some sense, I showed you the flip side of it today, but it's also algorithmically very useful, and therefore we care about it. And since it has been in some sense shown to capture many algorithmic techniques and leads to fast algorithms, it has been conjectured to be at least you could plausibly conjecture that it's optimal for some restricted class of problems. And when it is optimal, lower bounds on this particular proof system can be taken to mean some kind of a more general result, at least hinting towards the problem being hard in even like outside of the proof system. Okay. To end, I tried to give you a glimpse of why sum of squares is a promising technique for both hardness results and algorithmic results. But many important questions remain open. And therefore, with David Storer, I'm going to do a self-plug. I'm teaching a seminar on these techniques. Mondays 1:30 to 4:20 in Princeton University. Please do show up if you feel interested in any of these techniques. We can talk about any problems related to this.